Greetings, I'm Marian, a mechatronics engineering student from Monash. Today, I'll be presenting a model which is able to determine the optimal solar and battery size for maximum savings by using the mixed integer linear programming technique. Before we begin, I would like to state the motivation of designing this model. In our world today, accelerated global warming due to increasing carbon dioxide emissions is becoming a pressing issue due to its momentous effects towards nature. Ultimately, one of the largest contributors to this phenomenon is the increased burning of fossil fuels for generation of electricity to meet increasing global electricity demands. As such, the search for energy alternatives have led us to the discovery of renewable energy such as the harvesting of solar power, wind power, or hydroelectric energy generation. However, as of recent years, renewable energy only accounts for 15% of the total energy generation, whereas fossil fuels such as burning of gas, oil, coal, and traditional biomass accounts for 85% of energy generation. Hence, the escalating need for electricity generation will inevitably also increase burning of fossil fuels due to the slow adoption of renewable energy generation, especially in Malaysia. As shown here, the amount of solar irradiance in Malaysia makes it the perfect environment for solar generation due to our year-long sunny weather. However, the adoption of solar panels in Malaysia are slow. Research has shown that this is mainly due to the lack of awareness of the financial benefits and returns of a solar investment. Hence, if a good business model exists whereby both suppliers and adopters can benefit from the adoption of solar panels, reliance on burning of fossil fuels for energy generation can be reduced. With this motivation, the algorithm was designed using mixed integer linear programming (MILP) as a solver, where an objective function, bound by linear constraints, is maximized or minimized according to the problem modeled. MILP is a simple technique that can be used to optimize many optimization problems as it weighs the pros and cons of a problem in the objective function and finds the optimum solution according to the constraints of the problem. To determine the objective and constraints of the problem, initial assumptions must be made. Firstly, Malaysia's Enhanced Time of Use, also known as ETOU Tariff Scheme D, is effective for bill calculation. The ETOU is a unique tariff scheme applicable to commercial and industrial customers in Malaysia and has different rates according to time zones. As shown here, off-peak period in green occurs on weekdays 10 p.m. to 8 a.m. and 24 hours throughout weekends. Next, mid-peak period in yellow occurs on weekdays 8 to 11 a.m., 12 to 2 p.m., and 5 to 10 p.m., whereas peak period in red occurs on weekdays 11 a.m. to 12 p.m. and 2 to 5 p.m. Since the price increases across off-peak, mid-peak, and peak period, having an optimized solar and battery may reduce loads in peak period or shift loads from a peak to off-peak period to save cost. Aside from this, the total electricity bill also constitutes one other component, which is the maximum demand cost. The maximum demand is the maximum electrical power demand logged in a month. Hence, since maximum demand cost will increase 13% if it falls during the peak region, installation of a solar or battery may be able to flatten the sharp peaks and ensure the maximum demand occurs in the mid-peak region. With this, the total electricity bill under the ETOU scheme is the summation of bills in the off-peak, mid-peak, peak time zones, and maximum demand cost. Next, the sizing algorithms are also fixed to use 7 days of load consumption data with 30-minute interval as an input to find the optimal size of solar and battery. Moreover, it was also assumed that electricity cannot be sold back to the grid. Besides this, solar and battery parameters such as cost, lifespan, efficiency, and others are fixed as shown. It was also assumed that solar generation corresponds to the trends of a standard solar curve derived from averaging annual solar load profiles in Malaysia. With defined tariff structure and parameters, I now present the algorithm design. The solar sizing optimization aims to find the optimal solar size which gives the best bill savings and lowest payback years. Hence, it is designed such that the objective function aims to minimize solar costs and maximize bill savings. Solar cost, denoted as C solar, depends on the size of solar panel, S solar, which is an optimization parameter, whereas savings, denoted as R bill, is the original bill minus the new bill. Here, the new bill is calculated using the resultant load curve, denoted as P new, which is the original load curve minus the actual solar load curve. Since there is a possibility for flow back to the grid if extra solar energy is generated, this algorithm accounts for flowback of electricity to the grid through the variable C cell. C cell can be adjusted such that value of 0 would mean electricity cannot be sold back to the grid, and 1 would mean there is a 1-to-1 sell back rate to the grid. Finally, the constraints are defined as shown here, where solar size must be less than the maximum solar size desired. With the objective function and constraints, we have fully designed a solar sizing algorithm. Next, the battery sizing optimization aims to find the optimal battery size which gives the best bill savings and lowest payback years. Hence, the objective function is designed to minimize battery costs, inverter costs, battery degradation costs, whilst maximizing bill savings. Battery cost, denoted as CBAD, and inverter cost, denoted as CINV, both depends on the optimal battery and inverter size respectively. Next, battery degradation cost, denoted as CBAD, DEG, relates to the state of health, SOH. The state of health of the battery is determined by calendric aging and cyclic aging, denoted as aging CAL and aging CYC. Cyclic aging depends on battery flow, which is defined by P-BAD in, battery charging, and P-BAD out, battery discharging. Hence, battery charging and discharging are optimization variables, which is fully determined by the algorithm. All in all, battery degradation cost directly relates to battery charging and discharging, which allows this algorithm to produce a battery schedule to lower peaks and shift loads for maximum bill savings. Lastly, savings, denoted as R bill, is the original bill minus the new bill. Here, the new bill is calculated using the resultant load curve, denoted as P new curve, which is the original load curve plus battery flow. Finally, the constraints are defined as shown here, where it was set such that battery content must be full at 8 AM every weekday to ensure full capacity for peak shifting and shaving. Next, it is also set such that maximum demand must fall in mid-peak period instead of peak period. With the objective function and constraints, we have fully designed a battery sizing algorithm. Next, the solar and battery sizing optimization aims to find the optimal solar and battery size which gives the best bill savings and lowest payback years. Hence, all constraints and equations from the solar sizing optimization and battery sizing optimization are combined. With the exception of the removal of this equation from solar optimization and the removal of this equation from battery optimization. This is done because the resultant load curve is a combination of both solar curve and battery flow. With this, the combined result is shown here. The deleted equations from before are replaced with this equation, where the new load curve is defined as original load curve minus the solar load curve plus battery flow. Hence, the objective function of solar and battery sizing optimization minimizes solar cost, battery cost, inverter cost, battery degradation cost, while maximizing bill savings. To evaluate the performance of each algorithm, these measures will be used to evaluate the decision of the model, where monthly bill savings in percentage is the ratio of bill savings and original bill. Payback years is the number of years it takes for savings to accumulate to cover the initial investment cost. Lifespan net savings is the net bill savings after accounting for years taken to achieve payback years. And lastly, R ratio is defined as the ratio of lifespan net savings and payback years. This measure will be the primary indicator for value in the following tests conducted. Finally, allow me to discuss my results. For the sizing algorithm, tests were conducted on two different load curves for verification. For the first test case, data was taken from a rubber molding industry, where results from the sizing optimizations are shown here. In this test case, the most cost-saving option would be the installation of solar and battery, as it has the highest lifespan bill savings. However, if a customer wants the best value, which optimizes both payback years and lifespan bill savings, installation of battery only would be most favorable as it has the highest R ratio. For an in-depth understanding and verification of results generated, analytical analysis was done. As shown here, solar size of 1525 kW peak would be the most optimal sizing as it has the maximum highest R ratio. However, since the roof space only allows a maximum solar size of 1000 kW peak, the algorithm selects 1000 kW peaks since it has higher R ratio compared to the peak at 20 kW peak. Next, it is shown that only minimal electricity is flowed back to the grid. Now, battery sizing can also be verified as the R ratio plot shows a clear definite peak at 19 kWh, which is the result of the algorithm. It is worth noting that since we have included the battery degradation cost in the battery algorithm as shown previously, hence, as shown here, charging in blue occurs in off-peak and mid-peak period, while discharging only occurs in peak and mid-peak period. Also, it was ensured that battery content is full at 8 AM every weekday to prepare for battery discharging during the day to minimize peaks. Full battery content is also observed in weekends. This is because weekends are categorized in the off-peak time zone, making it unnecessary for battery discharge. With all this, battery optimization is validated. Finally, for solar and battery sizing, verification was done by fixing solar size and deriving the graph of R ratio against battery size. Once again, optimal battery size is similar to the algorithm results of 1000 kW peak solar size and 870 kWh battery. In test case 2, load curve from a machinery manufacturing industry was applied. Here, implementation of solar and battery provides most cost savings and value, as it has the highest lifespan bill savings and R ratio. Verification shows that optimum solar size is 130 kW peak, although algorithm results is 135 kW peak. Though an error, it is only a small margin where 130 kW peak also gives almost the same R ratio. Next, it is also worth noting that the algorithm allows flow back to the grid even though it cannot be sold back, because savings from maximum demand reduction of increased solar size exceed cost of electricity flowed back to the grid. For battery sizing, similar to test case 1, the algorithm produces accurate results for battery sizing optimization, with similar trends of battery charging and discharging and battery content, with full battery content occurring on every weekday 8 AM and 24 hours throughout weekends. Lastly, solar and battery sizing also produce accurate results as demonstrated here. This time, no flowback occurs as energy is flowed into the battery for charging instead. To conclude, mixed integer linear programming was used to design a sizing algorithm to make the best solar and battery sizing decisions for maximum savings and value. This presentation has also demonstrated the simplicity in using MILP technique to solve optimization problems. With the outcome of the sizing algorithm, suppliers and adopters would become more aware of the financial benefits of solar panel and batteries. This would lead to an increase in the adoption rate of solar technology in Malaysia. incentivizing banks to increase the availability of bank loan schemes for renewable energy adoption. All this will eventually benefit Malaysia's economy, environment, and its people in the long term. That is all for my presentation. Thank you for tuning in.